Question 6 from Paper 2 of the 2024 Higher Physics Examination from the SQA. A teacher uses the apparatus shown to demonstrate the deflection of a beam of electrons by a magnetic field. You can see the diagram there. We have a heater which supplies the electrons due to thermionic emission, and the electrons are swept across the electric field between the cathode and anode and in through the coils of a magnet, where the magnet deflects them up the way like that. You have an ammeter across here to measure the current, and you've got the potential difference here of 2.4 kilovolts. So the heater supply is used to heat the cathode, which causes electrons to be released from its surface. As I just said, the electrons are accelerated from rest towards the anode by a potential difference of 2.40 kilovolts. And we slide down, it says compare the diagram below, complete the diagram below to show the electric field pattern between the cathode and the anode. Now there we've got the cathode here, and we've got the anode, and we know it's going to have an electric field between the cathode and anode, and it's going to accelerate the electrons. But first of all, we must draw in the electric field. Remember, the electric field is always drawn in as lines like this. So we have one line like that. These stand for the electric field lines, and it's a uniform field like that. Now we've got to add in the direction of the field, and remember the electric field, I'll just draw another main line up here, because what happens up here, you get a kind of curve of the electric field at that point. You have to draw it precisely. Now, where's going to be the arrows for this electric field? Well, they always go from positive to negative, so the direction of the field lines are going to be like that there. So there's your complete diagram of the electric field. And you always can tell, because if you look at the electric field and you place a positive charge there, you can see a positive charge always moves in that direction. It moves in the direction of the arrows in that electric field. An electron does the opposite. It's going to move from the cathode to the anode. So that's your diagram for the electric field between the cathode and the anode. Question 6a continued, part 2. The gain in kinetic energy for each electron moving from the cathode to the anode is 3.84 times 10 to minus 16 joules. And for 3 marks, it has to calculate the maximum speed of an electron as it reaches the anode. Well, we know it's moving from rest, so its final kinetic energy, we don't need to add any kinetic energy on because it started off from rest, where its kinetic energy is 0. So we have the kinetic energy formula, EK, and that's going to equal to 1/2 times the mass of the electron times the speed of the electron squared. And that's what we're trying to find, the speed. So undo this equation, and we multiply each side by 2 to get double the kinetic energy is equal to mv squared. And then we divide each side by m, the mass of the electron, and we're left with v squared. Finally, we have to take the square root of v, and that means we're going to have to take the square root of twice the kinetic energy divided by the mass of the electron. So just to have to put those numbers in, we know the following. We know that the mass of the electron is 9.11 times 10 to the minus 31 kilograms, and we know the kinetic energy value from the question. So all we have to do is plug in those numbers, and we have the following. We have V is going to equal to the square roots of twice the kinetic energy, put that in brackets, twice times 3.84 times 10 to the minus 16, and bracket that, divided by the mass of the electron, which is 9.11, which we get from our data sheet, times 10 to minus 31 kilograms. Now, if you actually do that on your calculator, you end up with a speed of 2.90 times 10 to the power 7 meters per second. And that's the speed the electron achieves at the anode. Question 6a, part 3. The cathode and anode are separated by a distance of 45 millimeters. Calculate the maximum acceleration of the electron between the cathode and the anode. Well, we have to put down all our kinematic rules, our variables. We have u, the initial velocity, v, the final velocity, a, the acceleration, s is the displacement, which in this case is the distance across from the anode to cathode, and time t. So we put in first of all u, we assume that the electron is starting off from 0, from rest, so u becomes 0. Its final velocity, we just calculated there now, was 2.90 times 10 to the power 7 meters per second, and we've got to find its acceleration. The displacement that occurs in, the distance that occurs in, is going to be 45 millimeters, but be careful, it's going to be 45.0 times 10 to the minus 3 of a meter. You must keep everything in meters time. We don't know anything about the time. So we have got U, we've got V, we have to find A and get S, and it looks like we're going to use this equation here. V squared is going to equal to U squared plus 2 times the acceleration times the displacement. Now you should be well practiced at rearranging this one, and we know that if we rearrange we get V squared minus U squared, put that in a bracket, that's going to equal to 2A times displacement. We're after acceleration, so we have to divide both sides by 2 times the displacement. So V squared minus U squared all over 2 times the displacement is going to give us the value for the acceleration. So putting in the numbers, we have got in this case 2.90 times 10 to the power 7, and we're going to square that, and because u is 0 we can just forget about that. It's going to be take away 0, so we can leave that, and divide by 2 times the displacement, so bracket 2 times 45.0 times 10 to minus 3, and if we do that we get an answer of 9.34 multiplied by 10 to the power 15, and it's an acceleration meters per second every second. Question 6, continued part B. A small hole in the anode allows a narrow beam of electrons to be produced. The beam of electrons passes into a uniform magnetic field between the coils. The diagram shows the path taken by the electrons in the uniform magnetic field, and for just one mark we have to determine the magnetic field direction. Is it into the page or out of the page? Well, let's take a look at a simulation of what's happening. We can bring our simulation over. There's the electron going into this magnetic field, and you can see it's following the same direction as the one in the question. So we look at the magnetic field and it must be coming out of the screen or out of the page. We can use a right hand rule for that, because remember it's an electron, so we use our right hand rule, and very hard to show you on here, but I think you can use the right hand rule to prove to yourself that the magnetic field will be coming out of the page.